Basic probability. Here's a question to ponder from the media viewing that you did already when you come in here. What is the probability that we get out of class late? Okay, that's a number. Plus the probability that we get out of class 0 minute early. That is not early at all and not late. Plus the probability that we get out of class 1 minute early. Plus the probability that we get out of class 2 minutes early. Plus the probability that we get out of class 3 minutes early. Plus the probability that we get out of class earlier than that. Our plan for today. Well, we're going to continue pondering this question about the sum of all those probabilities. There's going to be a skeleton lecture in the whole group space on basic probability and an activity, partial group space, and a 1-minute exit ticket activity. Our objectives are to compute theoretical probability and to compute empirical probability. So one word difference there. Probability is likelihood on a scale of 0 to 1. That's what it is. Likelihood. And the scale is 0 to 1. So probabilities are assigned values from 0 to 1, inclusive. The closer the probability of a given event is to 1, the more likely it is that the event will occur. The closer the probability of a given event is to 0, the less likely that event will occur. So if your event has probability 1, that might be like the probability that I see a duck today. And then likely would be the probability that I see a goose. 50-50 chance. 1/2 would be the probability that if one of those geese wanted to take me out, that he could. It'd be a fair fight. An impossible event, that would be the event that the Aggies win the Final Four. And an unlikely event. An unlikely event might be that I would actually see the mullet duck that one of my students drew. Mullet duck loves him some math. And notice how it says WUC on his chest. The WUC, the warm-up close activity. So he's the duck of the activities that we do, like the one we'll have today. The WUC duck. Theoretical probability. Okay, so some terms that we have to define having to do with theoretical probability. An experiment is a controlled operation that yields a set of outcomes. So sometimes we talk about experiment. What do we mean? That's what we mean. A sample space is the set of all possible outcomes of an experiment, denoted by the letter S. Sample space. That's important. Notice how it's a set. So since it's a set, there are things that we say about sets and can only say about sets. And those kinds of things are appropriate when talking about sample space. And one of those things is about the word event. And an event E is actually a subset of a sample space. So since the sample space is a set, it's appropriate to talk about a subset of it, and that's how we're defining event, which we're going to talk about a lot. Question: what is the probability that if I were to flip a coin, the outcome would be heads? Not too tough. If an event E has n of E, the number of outcomes in event E, n of E, equally likely outcomes, and its sample space S has n of S equally likely outcomes, the theoretical probability of event E, denoted by P of E, it's not P times E, it's P of E, like f of x, is P of E, probability of E, it's a quotient, it's a division, number of outcomes in event E, n of E, over the total number of possible outcomes, n of S, the number of things in the sample space. So it's that ratio. So again, what is the probability that if I were to flip a coin, the outcome would be heads? Well, you've got one success, one thing in the set, event E, and two possible outcomes, two things in the sample set, because there are two sides of the coin. And so sample set is the set heads, tails. N of S is 2. N of E is 1. The event head, which that's the only thing in the set. So 1 over 2, 1/2. Now, an objection might have been, well, what if it's a rigged coin? What if it's not a fair coin? And so we have to specify that we're talking about equally likely outcomes. If each outcome of an experiment has the same chance of occurring as any other outcome, they are said to be equally likely outcomes. And of course, that is the belief that we have when we flip a coin, say at a football game. Everyone's kind of believing in the fairness of the coin. They're believing in equally likely outcomes, because when people decide whether they're going to call heads or tails, they're not thinking, well, there's probably more surface area on the head side of the coin than on the tail side of the coin. They're probably not thinking that. And so they're just thinking, you know, that one side or the other is their lucky side, or whatever. There's some other reason why they pick what they pick when they call a coin toss. Well, there's looking at a coin and thinking about a coin, doing what we just did, which was considering the nature of the coin in order to come up with the number 1/2. That's theoretical probability. We were theorizing about the experiment of the coin toss. But then there's empirical probability. And empirical is just a word that means experiential. It applies to situations in which we observe how frequently an event occurs. Computing empirical probability, the empirical probability of event E is, and it's a similar ratio, it's trying to get at the same thing, really. Observed number of times that E occurs, so number of successes divided by the total number of possible outcomes, the total number of observed occurrences, in our example, heads and tails. But here you're actually flipping the coin. And so we're going to flip the coin and see what kind of results we get, and we'll stipulate probability based on that. We might use a random coin flipper to speed up the process. You can go to random.org to do that, or you could use the one coin flipper, but then again you could flip any number of coins using the random.org coin flipper. From what I've seen, though, you would actually have to count them. Once you had, I mean, you could flip 100 coins at once, but you would actually have to sit there and count the number of heads. They don't do that for you, as far as I could see. Maybe the results would go like this. This says 4 out of 10. We got whatever number we got. Maybe if we did that 100 times, we would have 45 heads. 1,000, maybe we would kind of hit a hot streak and come up with 546 heads. For a relative frequency, the portion of times that it occurs in decimal form, 0.546. Maybe if we did it another 9,000 times, the number of heads would bring us to a relative frequency, or an empirical probability, of 0.4852. And maybe it would be likely that the result would be something like this. Another 90,000 to bring us to 100,000 observations, and 49,770 heads. And there's an observation to be made about these numbers: 0.4, 0.45, 0.546, 0.4852, and 0.4977. Another example. Selecting one card from a deck. A standard deck of 52 cards is shown. When doing probability problems, you really have to know a deck of cards. And some people just know it, and some people just don't know it. But those of you who don't know it, you'll have to learn it to do these probability problems. Now, there's a limited number of kinds of probability problems that we have: coin flipping, die rolling, cards, and spinners. But as you can see, there are 4 what we call suits: hearts, clubs, diamonds, and spades, and each suit has 13 cards in it. Ace through 10, where the aces are usually counted as ones, but then you have 3 what are called picture cards: jacks, queens, and kings. So the jacks, I mean, these are called picture cards or face cards because they actually have faces on them. The one with the old man is the king, and the one with the woman is the queen, and the one with the young man is the jack. What is the probability of, if you select one card from a shuffled deck so that the outcomes are random, what is the probability of an 8? Well, as you can see, there are 4 8s in the deck, and there are 4 times 13, or 52 cards in the deck. So 4 over 52, which reduces to 1/13, is probability of 8, P of 8. What's the probability of not an 8? Well, you could count all the things that aren't 8s, and you would, if you counted accurately, you would have 48 things that aren't 8s. And there's still the same total number of possible outcomes, 52. So 48 over 52, or 12/13. And you might have in mind a computation that could be made based on your answer to A to get the answer to B without actually having to count all the non-8s in the deck. Probability of a club. Well, I see 13 clubs there, 13 successes, 52 possible outcomes. Probability of club is 13 over 52, or 1/4. What is the probability of a jack or a queen or a king? That is a picture card. Well, I see 12 successes out of 52 possible outcomes. So 12 52nds, which reduces to 3/13. What about this event? Subset of the sample space. A picture card or a club. A picture card or a club. Okay, well, let's see. I could start with the picture cards and then throw in a bunch of clubs that aren't also picture cards and come up with 22 of those, right? Because you'd have the 12 picture cards and then you'd have the 10 non-picture clubs, ace through 10. That'd be 10 plus 12, that'd be 22. Or you could say, let's just count all the clubs. That's 13. And then all of the non-club picture cards, you'd add 9 to the 13, that'd be 22. So it looks like there are 22 successes in the deck. You could just count them all and get 22. 22 52nds reduces to 11/26